Recording is rolling. It is Tuesday, August 20th. So today's been a little bit different each class because, okay, there's this infrastructure trial in period two. It's been a little bit of a flex day. So I've been getting everybody up to speed on trigonometry and these different ways we're going to do it. Okay, now you guys remember I had assigned you guys this trigonometry puzzles few days, about a week back, right? And I had a due date today. Right? So a lot of students, they'll get on this and they turn this into the grade tray. I see grade tray over there, and I'll start grading those. Right? Now, guys, there have been students in each of my classes today that just, handful of students said like, this hasn't quite clicked yet. They've been working on it. It's not quite coming together. So guys, if you need an extra day to do this, it's okay if you turn this in tomorrow. Okay, so I can push this back one more day. Right? If you don't feel 100% about it, you can turn it tomorrow. It's okay. Right, so, and I want to do review with you guys anyway. So we're going to be doing more this vector components because I really want you guys to know this because this is going to keep coming up in physics, right? So vector components. Okay? So what else we got going on? First, there was that infrastructure trial. So yeah, my period two, we're mostly doing that. We're going to do Kahoot. So you guys log on Kahoot for that. Right. I do have another Kahoot lined up for algebra. So I'll get kind of a feel later on in class if you guys want to do algebra Kahoot. We might do that. Take a few minutes. Okay? And I do also. I gave you guys, or if it's not one on your desk now, I've got a stack of these templates. So yeah, I do have this rainy day activity. So if you guys feel really good about trigonometry and nobody needs a lot of help on that, we might, yeah, I got a special kind of calculator that we might be later. All right, so you guys go with the agenda, kind of what we're doing? All right, so here we go. Let's do a quick review, because you need to see this a few times, right? Like some of you guys might have seen this in a math class in the past, but there have been a number of students that are just seeing this for the first time, like starting last week. Yeah, if you see it multiple times for multiple days, then your brain can start to process it. And so it goes like this. We're talking about vectors and vector components. That's why it's called vector components. Okay? So most of the time in physics, it works something like this. Like there's some vector, say this could be a force vector. Maybe I'm pushing up to the right, with some force. But I want to quantify like how much to the right, right? Or maybe you've got a string with some tension in it. So well, how much is it holding up and how much is it pulling over to the right? Right? And that's what these two boxes are here for. Right? Where does it come from? Well, the definition of sine, cosine, and theta. So these are straight out of a math textbook. But I rearranged them a little bit. How you see it like almost all the time in physics. We're about to do a Kahoot that's mostly these two boxes right here. Right? So if you have the original vector at some magnitude at some angle, take that vector times sine of that angle, it gives you the opposite leg. In this case, how much up? Take that original vector times cosine of this angle, it'll give you the adjacent leg. In this case, how much over? Right? That's pretty much it. Right? How do you see it in physics? Right? It could be any kind of vector. I did a force vector, but it could be a displacement vector. What if somebody's walking northeast, across a huge field? How much north and how much east? Well, it depends on the direction they were going. That's just sine and cosine, right? Or what if there's a plane flying northeast at some speed, right? And I want to say, well, how fast is he flying strictly north and how fast is he flying strictly east? That's just sine and cosine. Boom, boom, boom. Right? And finally, you're going to get a couple of questions that have you guys solve for this angle theta. Okay? So if you have lots of side information, you can use an inverse trig to solve for the angle. For example, if you know the two legs, you can take the ratio of those two legs, take inverse tan of that, that'll spit you out the angle. You guys see you can take a sine, cosine, or a tangent of an angle. It will be defined as some ratio. Or, like this very last box, you can take an inverse trig, like an inverse tan of a ratio. That'll spit you out an angle. Okay? Great. You guys ready to do that? All right. So let's flip over to Kahoot. All right. And you guys are all logged on, ready to go. All right, here we go. It is test time. You guys know your stuff. So see 100-meter hypotenuse. It's like some guy walking across the field 100 meters kind of northeast, mostly northeast. Did you guys do 100 times sine of 75 degrees? Is that what you did? Yeah, that is what you did. All right, so again, like most of these, especially today, I'm giving you the hypotenuse. So you start with that. You plug in that number 100. Let's get 100 meters. Multiply by, and you want the leg that's opposite of the given angle. So opposite of 75 degrees, well, that's a sine relationship to translate from hypotenuse to opposite. Okay. All right, got points on the board. All right, got got Hunter. We got the pin number. We got Peyton, Olivia, and Zach. All right, solve for x. Hey, it's the same triangle. And now you're solving for x. How far did the sky walk strictly east? Not very much. Did you guys do 100 times cosine of 75 degrees? Right? Right? 100 times cosine of 75 degrees? Ah, okay. You guys see that? You see that? Right. We're going to do a bunch of those. Right. So if you're like a little rusty on that, okay. We're about to do a bunch of those. I got Hunter, Isabel, Olivia, Peyton, Zach. Did you guys do 100 per second times sine of 45 degrees? 100 sine 45? Yeah. Okay, you guys go with that? Okay. Ooh. Did you guys do 100 times cosine of 45 degrees? Yeah. Hey, is that the same answer as before? Does the last two questions have the same answer? Right. Let me point something out to you guys, because guys, that was actually a what kind of special right triangle? 45, 45, 90. That's right. Let me guys show you guys some notes from last class. Here's three special right triangles. It's not the only three, but you see these quite a bit, right? So you guys just saw this one here, right? So 45, 45, 90, isosceles right triangle, right? So the sine of 45 degrees or cosine 45 degrees, that's going to give you the same thing either way. That's the only one that works like that, right? Mix up sine cosine. But these other ones, all right. You guys heard of what is this called? A what triangle? 30, 60, 90. And I listed the side. So this is side length 1. Hypotenuse is always double that. And then this side is square root of 3. Okay, so you got that. Right. And then, here's a 3, 4, 5 right triangle. Okay. What if you forgot those angles? You're like, I forget what angles is down there for a 3, 4, 5. Here, let's solve this angle. Let's pretend you don't see any angles here. How do you get this angle? Do second tan, like an inverse tan of opposite over opposite over adjacent, I might say, right? Opposite over adjacent, right? Is this going to be this angle right here? Yeah, there you go. Okay, so every one of those triangles is different, right? So sometimes people mix these two up, but these are different from each other, right? All right. All right, back over here. Back to Kahoot. So how we're doing here? Oh, we got Ian, Isabel, Peyton, Zach, Olivia. Number 5. So maybe that's a like 100 newtons times sine of 30 degrees. It sure is. Hey, that you guys are seeing it now. What is sine of 30 degrees exactly equal to? 1 over 2, 1/2, right? Sine of 30 degrees is exactly 1/2. It's probably a good tidbit to know. Okay. Half of 100 is 50. Zach to the top spot. Oh, you guys notice too how the hypotenuse is a solid vector and the components are dashed yet? I especially emphasize that with the AP exam. They have to draw it that way. But the idea is that if you made them all solid, you'd be double counting vectors. Say, I'm pushing that way and that and that. So like you got 3 forces going on. But no, I got 1 force. I'm splitting it into components. Okay, so you guys got that? Right, 100, or so, okay, so All right, Peyton, to the top. I got 100 Newton. Maybe that's a weight vector. Maybe that's what they could be. Pulling straight down, that's hypotenuse. K2 times sine of 40 degrees, because the leg Y is opposite of the 40 degrees. Again, notice those components were dashed. Those components were dashed, right? Not solid, but dashed, right? So you guys did 100 times sine of 40 degrees, I think. All right. All right, Olivia, back to the top. Let's do 100 newtons times cosine of 40 degrees. That specific scenario, you're going to see, like if you put a block on an incline, you're going to see that orientation looking over a right triangle shape. Right? The vector components. All right. All right. Any questions so far? All right, you guys getting these? All right. All right. Got Isabel, Ian, Zach, Peyton, Olivia. Number 9. You guys do 100 newtons times sine of 60 degrees. All right. All right. There you go. All right. Alexander in the top 5. Olivia still in the lead. Did you do 100 newtons times cosine of 60 degrees? So, all right. Is there any question how it's getting the answer? All right. Okay. All right. You guys do see this posters hanging over my lab closet door too, right? Trying to play off that one. All right. I think we got 2 questions left. Oh, Ian moving up. Peyton second. Olivia first. All right. Solve for theta. How many guys did inverse tan 20 over 21? Yeah. All right. Okay. Right. So if I'm playing off the 2 legs, it's got to be inverse tan. You could also do inverse sine or inverse cosine off different set, but kind of directing you guys toward inverse tan and then opposite over adjacent. Right. All right. Peyton taking first place and for the win. For the win. So you could do inverse tan 13 over 84. Let's do that. Inverse tan 13 over 84. Yeah. All right. And of course, all those you guys saw, all those examples had units attached. Like that was newtons, but just don't put the unit in the calculator, just the number. All right. All right. So you guys good? All right. You guys all right? All right. All right. Let's see here. All right. With the bronze, Zach. With the silver, Livia. And the gold, Peyton. All right. Got runners up. Got Ian and Alexander. Nice job, guys. Right, let me pause this recording and ask you guys what you want to do next here. All right, we're back recording. So we're gonna do algebra Kahoot. That's what we're doing. Algebra Kahoot. Here we go. You guys got paper, pen, pencil, calculator ready? All right. Should say some of these. I think I let the clock run a little too long. I might stop the clock a little early on some of these, but we'll see how you guys do. Square root of x is 10. Solve for x. you square both sides? So x would be 100, right? Square root of 100, that's 10. Hey, that works. That works. All right, all right. All right, we're off to a good start. Points. Solve for m. Can you square both sides? So that'd be 100 on the left side. Then what's the next step? Cross multiply the 10. So it'd be 100, because 10 squared is 100, then multiply by 10. That should be 1,000, right? Okay. You can also start from the answer and plug it in and see if it works. So guys, what's 1,000 divided by 10? 100. And what's the square root of that? Equal to 10. And that was the original setup, right? So it checks out, right? So you can either undo every step that's there. That's what algebra is, right? Plug in the answer and see if it works. We got Zach, Hayden, Isabel, Alexander, Olivia. Solve for V. You square both sides, then add 4 over, right? Okay, so square both sides, 3 squared is 9. Then you add the 4 over, that gets you to 13, right? Or you could work back. So 13 minus 4 is 9, square root of 9 is 3. Ah, yeah. All right, Isabel, top spot. So square root of 5, got like 36, and then add 2, I'll get you to 38. Okay, so to undo each step at a time. So you square both sides, 6 squared is 36, then add the 2 over. All right, got John, Luciana, Peyton, Zach, Isabel. Okay. Square both sides. I think you got the answer. There you go. 9 squared, 81. Oh, yeah. Oh, yeah. Lots of points. Oh, yeah, that's fine. It says 5 equals square root of x plus. Okay, okay, so square both sides. Guys, what's 5 squared? 5 squared is 25. Then subtract the 3 over. What's 25 minus 3? Okay. Okay. So I don't know why that one turned out like that. Oops. But, right. Okay. All right. So let's get that. Square root of 4 is 2. There you go. Lots of points. Square both sides. What's 1 squared? Subtract 9. What's 1 minus 9? Okay. All right. John, Luciana, Zach, on fire, Peyton, Isabel. But 9. What's negative 3 plus 8? That'd be 5. To square that, what's 5 squared? 25. 25 plus 5 is 30. What's 30 divided by that last 5? Okay. A few steps there. All right, here we go. We got, all right, John, Luciana, Zach, Peyton, and Isabel. We're going for the win. You guys ready for the win? It's for the win, for the win. So divide both sides by 10. That gives you 6 on the right side. And you do what both sides? Square both sides is what's 6 squared. 6 squared is 36. Then the last step is to divide both sides by 9. It's 36 divided by 9. Ah, okay. I'm gonna stop this a little early. 4. Okay. Okay, guess that. Fix the clocks on those. All right, to the podium. The podium with the bronze. Zach. With the silver. Diana. And the gold. Isabel. All right, nice job. Oh, and where's up? John and Peyton. All right, recording resume. So one last quick review here. Okay, so on these 10 trigonometry puzzles, I gave you some information about right triangles and just enough information you can solve everything else. Okay, and really what you need, this is probably the most important poster right here. This will help you navigate most or all of everything. Okay, these type of relationships. You need to do some algebra shuffle somewhere. If you're not sure, here, if you got the 2 legs relationship, that's always something to do with tangent. If you have reference angle opposite hypotenuse, that's always a sine relationship. If it's reference angle adjacent hypotenuse, it's always some cosine. You can always set up any one of these and then do some algebra and solve for what you don't know. Like if you want to solve for C, you could rearrange it this way and then divide this cosine theta down. Okay, right. Pythagorean theorem could be helpful, right? That can help you. Also, you guys know that the 2 acute angles, right, the 2 small angles, in this case alpha and beta, always should add up to 90 degrees. So if one of them is 30 degrees, the other must be 60. Right. So there you go. There's a quick recap of some details. Right, we're going to move on to this calculator activity. Right, so you guys are cutting out the 2 circles. Right, I'm cutting out the 2 circles. You guys cut out the 2 circles. Right. Let's look at this while we're cutting these out. So, do you guys notice how the numbers are spaced? Like the numbers on these circles, they go from 1 to 9, and then it wraps back around to 1 again. You guys see that? Right, 1 to 9 wraps around. So I don't see really 2-digit numbers, and so right. And the numbers aren't really evenly spaced either. You guys see how there's a huge gap between the 1 and the 2, and then from the 2 to 3. Oh, so here's 1 to 2 gap, and then 2 to 3. It's a little closer. 3 to 4, it's a little closer. Oh, then now they're getting successively closer. By the time we get to like 7, 8, 9, it's real fast, and then we're back around to 1, and there's a huge gap all the way to 2. So guys, these numbers are definitely not spaced linearly. They're not spaced evenly linearly. Right? They're spaced how? Who has a guess? There's a reason they're spaced the way they are, and it's not a linear spacing. It's a not quadratic. You guys ever heard of exponents and logarithms? Right? I'm going to call this logarithmic spacing. Earlier, some students said exponentials, which is really the opposite side of the same coin. So exponents and logarithms are like the exact opposite process to the same idea. Right? So yeah, so it's like exponential or logarithmic spacing. Okay. Now why? What's that going to be good for? Well, you will see. You will see. How about this? Let's go back to 1970. You guys are working for NASA. We're blasting rockets off to the moon. We're sending astronauts up to the moon. Is that true? Back in about 1970? Okay. Hey, do you guys think back in 1970 they were, do you guys think it takes lots of calculations to send people up to the moon? Lots of calculations, right? Did they back in 1970 have these very convenient pocket-sized digital calculators? No. If they had it, the closest thing is maybe like, maybe big old room size calculator, and then you have to like reserve time on it and stuff. So right, maybe a little bit, but they didn't quite have this. Right, it'd be really nice if they could pull this out of the pocket, but they don't have that. Because what did they have? If they didn't have these digital calculators, what did they have? What were they doing calculations with? guys ever heard of a slide rule? A slide rule? Yeah. All right, so I don't have one. I was just trying to find one. They're kind of hard to find nowadays. Right? But it's like two rulers you clip into each other and they slide past each other, right? But the numbers on the rulers are not spaced evenly, linearly, like they are on this actual ruler, like the 1, the 2, 3, 4 are spaced evenly on this ruler, right? On a slide rule, they're spaced, guess how? Logarithmically, just like these circles. Hey, if I had like two rulers that were logarithmically spaced numbers slide past each other, this is two circles. They're slightly different sizes. Guess what we're about to make? A slide rule calculator, but a circle version. This could be a calculator. By the time you guys walk out of class today, you're going to be able to take these pieces of paper. You'll be able to take square roots, multiply, and divide. Okay. By the time you walk out, okay, guys, see a little hole in the middle? Let's punch a hole where that dot is in the middle. Punch a hole. And this one, punch a hole. You guys got a couple of holes? Yeah, some paper clips on your desk. Maybe that could be helpful. Punch those holes. All right. You guys punch a couple of holes. Right? Now, what eventually here, let me show you guys this model we're eventually doing. Eventually, you're gonna slide the paper clip through and use the paper clip as an axle. See how this could be an axle? You could slide like this. Is that right? Right. Now, I'm actually not quite gonna do that yet because the first function I want to show you with each of these is how to take square roots. And for that, you don't actually need both circles. You only need one. So and it could be either one, and I'll show you guys why it could be either one. If you lay them right on top of each other, and go ahead and do this like I did, put one right on the other, and align the 1 and the 1. You guys see the 1 and the 1 are aligned? And when you do that, all the other numbers pop in place. The 2 and the 2 are aligned, the 3 and the 3, and all the way around, the 7 and the 7. See how all the numbers pop in place? Okay. But what I'm trying to get at is that two circles are the same. Okay, the numbers are spaced the same. Right? All right. So now that you know that, pick one and put it to the side and pull out the other one. We're going to use either one because they're the same. Right? Okay. Now, what does this have to do? The fact that the numbers are spaced logarithmically, how does that help you take square roots real fast? Well, let's talk about square roots and exponents that we'll do. Right? So, for example, here, let's start off. How about square root of 9? Right. Guys, what's the square root of 9 equal to? 3, right? So just 3, right? And there's another way to write square root. That's so square root of 9. I could call it 9 to the power of what? 1/2. A 1/2 power. That's the same thing as a square root, isn't it? Right. Let's do a few of these. How about what's the square root of 90? What's that? Might need a digital calculator for this one. 9.48 and a string of numbers. I'll round that to 9.49. Not exactly, but pretty close. Okay. Okay. How about this? What's the square root of 900? What times what is 900? 30. Right? How about what's the square root of 9,000? $94.9, I bet. Right? I know 100 times 100 is 10,000. It's a little bit less than that. What is the square root of? I want you guys to see a pattern here. Who's going to figure out this pattern? What's the square root of 90,000? 300. What's the square root of 900,000? 949. I bet it is. Right. So do you guys see a pattern? Right. There's like an odd track and an even track. Go back and forth. Right. Right. So okay, what does this have to do with this paper? Right. So guys, for square roots, here's what we're going to do. I'm going to treat the number 1 as home base. You guys see a number 1 up here? That's my home base. Right. Right. Now my target number, let's say in this case, could be 9. So I want to take the square root of 9. Right. Right. Now, guys, what was square root as an exponent again? 1/2. Right. Do you guys think it's going to represent halfway around the circle with number spaced logarithmically? I bet it is. Let's go halfway around the circle. Bing! It's right here. It's here. If I go from the 1 to the 9, exactly halfway around the circle, that is this. Right. Oh, look at this. Look at this. It's exactly 3. You guys see it's exactly 3? It's exactly halfway around the circle between 1 and 9. That's how you know square root of 9. Now here's the thing though, is the numbers only go 1 to 9. So what about all these other roots, right? Well, think about it. The decimal place is allowed to float. So the number 1 might represent 1 or 10 or 100 or 1,000 or a million or maybe 0.1 or 0.01. And same thing for any of these other numbers. Like 9 might be 9 or it might be 90 or 900 or 9,000 and so on. Is it? So when you're doing these calculations, you do have to keep track of in your mind what's a reasonable order of magnitude, right? So, and then this calculator is just going to tell you the digits, and you have to figure out where the decimal place goes. Okay. Okay. So I could say square root of 9 is 3, but it also answers all these other odd tracks, like square root of 900, square root of 90,000. Right. That's also so being 30 and 300 respectively. That's all the same thing. It's halfway between 1 and 9. The long way around the circle. But you know what? You might be looking and say, hey, isn't there also a short way halfway between 1 and 9? Let's go, bing, then you're done halfway between 1 and 9. And guess what number? See if you guys are following. Is exactly halfway between 1 and 9 the short way. It looks like maybe 9.5, but you know it's not 9.5 because it's not linearly spaced. 9.49. Right? Oh, because that's like the even track. That's the square root of 90, square root of 9,000, and square root of 900,000. So point. Okay. So now you guys can do roots, right? Yeah, you guys got to keep kind of a reasonable idea of what would be what. Should I go this way around or this way around? Okay. Is it? Let's do it for 1, 10, 100,000. So square root of 1, square root of, I'll set up a bunch of them. 10, 100, 1,000, 10,000, 100,000, and a million. Let's do all those. All right, so it's like so square root of 10 isn't like 10 to the power of 1/2, right? And square root of 100 is 100 to the 1/2, and so on. Going. Right. Okay. See if you guys see a pattern out of this. Guys, what's the square root of 1? 1. What's the square root of 10? Anybody know? You try it out. I bet you'll get something like that. 3.16. You guys say? Okay. It's the square root of 100. 10. Square root of 1,000. 31.6. Square root of 10,000. 100. Square root of 100,000. 316. Square root of a million. 1,000. Okay, so you guys see a pattern again, right? Okay. Let's see, does that also work on this? Kind of like we did for 9. Does it work for 10? Okay, so my 1 is my home base, and the 1 could represent 1, or could represent, actually, I guess any of these also, right? 10, 100,000, and so on, right? So, guys, this time, what's the short way between 1 and itself? Would just be itself, wouldn't it? You don't have to move anywhere. Okay, that's this odd track now. We got square root of 1 is 1, square root of 100 is 10, square root of 10,000 is 100. Okay, that's the square root. But what about the long way around the circle? Because what's halfway between 1 and 1? Halfway, wouldn't that be exactly like 180 degrees around the circle? I can just whip off a line with this ruler, go, zzz, I see it. Guys, what is that? Right there. 3 point what? 16, 3.16. You see it's 3.16? So be square root of 10. Is that? Okay. So now you guys can take square root. Let's do cube roots. You guys think you do cube roots? Okay. Let's do how about the cube root of 8? Because what is the cube? Oh, as an exponent, what is that? That's 8 to the power of what? 1/3. Right? Hey, do you think that's like 1/3 of the way around? Right? Let's see if that works. So here's 1. That's my home base. Here's 8. I want to take the cube root of 8. Now, cube root should only be 1/3 of the way around. Let's go 1/3 of the way. It's probably about, I'm going to kind of estimate with my thumb. Is that probably right about here? What does that say? 2. Hey, is that true? Is that true? Is that what this is? I think that's true. Because 2 times 2 times 2 brings you back to 8. Right? What about, can you guys do, how about 8 to the 2/3? Is that just 8 to the 1/3 and then squared? Because what is 2 squared? 4? Right. And see, is that also 2/3 of the way around the circle? Here's my home base 1. Here's my target 8. Let's go 2/3 of the way around. Is that like my left thumb? It is 4. It is 4. 4. Bing. Okay. Right, so you guys can do roots. You guys do roots. All right. You guys ready to multiply and divide? All right, so multiply, divide. Right now I'm gonna need both circles. I need a couple of circles interacting so I can get two numbers either multiplied or divided. Right. It's just through. All right. All right, so let's start simple, something that you could obviously know just to test this out and make sure that it actually works. Right, and then we'll do something a little bit more tricky. Right. So how about this? Now remember, I showed you guys before. The numbers could align, so I could align. I'm gonna use this as a model. I think got a little bit better axle here. Right. I'm gonna align the all the numbers. So the 1 and the 1, and then everything else locks in place. The 2 and the 2 align, the 3 and the 3, 4 and 4, and so on all the way around. Right. Right. So now I can rotate. What if I align the outside 3 with an inside 1? You guys see an outside 3 and an inside 1? You guys see that right there? Right. I'm going to treat that as a fraction, like a ratio. Call it 3 over 1. Okay. You guys get that? 3 over 1? All right, okay, so now what? So great, I got a fraction. Okay. Now, if you lock the circles in place relative to each other and look around the circle, what you'll notice is that, well, let's see what we notice. Right. Okay, so here I see a 6 over 2. Hey, is that the same thing? 6 over 2? It's the same ratio. All right, rotate a little bit more. Ooh, what is this? What is 9 over 3? Is that the same ratio? Right. You guys think it's the same ratio all the way around? All the numbers, and that'll always be true. You can always rotate the circles however, and the ratios are always the same. Right? Oh, wait. Am I lying to you guys? What is this? What is this? 1.2 divided by 4. Does that work? Decimal place is allowed to float. Can you interpret that as 12 over 4? I think you could. You're allowed to float the decimal place. You guys remember that? That could be 12 over 4. Okay, so the ratios work. Right. Now that the ratios work, you guys know what the ratios work? Okay. I'll show you guys how to divide. Right. Let's make pretend that you don't know what 6 divided by 2 is. Obviously, you know it's equal to 3, right? Right. But we're going to use that to test. Right. And maybe come up with some kind of pattern, right, that we can use to divide anything later on. Right. What is 6 divided by 2? Well, let's try it out. So I'm gonna rotate this so I have an outside 6 and an inside 2. So there's my question. So, I wonder what 6 divided by 2 is. Right. Well, I know it's equal to all the other ratios around the circle. Hey, one of those ratios very conveniently has a denominator of 1. Anything divided by 1 is just that number. Hey, I think that the inside 1 is always going to point to the answer, to whatever you want to divide. Is that true? What is 6 divided by 2? Align my 6 by 2. Lock those circles in place relative to each other. And say, what does the inside 1 point to? It points exactly to 3. That's the answer. 6 divided by 2 must be 3. All right, let's do, here, somebody give me a random 2-digit number. 43? All right, how about another 2-digit number? 27? What is it? There we go. So 43 divided by 27, okay? All right, so what could that be? Well, first I want to get kind of a ballpark order magnitude idea, right? But it's probably a little bit less than 2. You guys think a little bit less than 2? So I know it's not 20 or 200. It's probably maybe 1 point something. Okay. Right. Let's see. So I need the outside 43. So that could be 4, 1, 2, 3. Remember 4.3 and 43 are okay. Both that tick mark is there. I need an inside 27. So I'm going to rotate. Right. So I need to be all right. So there's 27 there. 43 is there. All right. Make sure these are aligned. All right. I'm going to try to get this right. Okay, here's 43, here's 27. 43 over 27. Bam, that's that notch right there. You guys go with 43 over 27? Right? Right. Now, of course, the ratios are the same all the way around. Right. What does the inside 1 point to? So I'm gonna have these circles locked in place. Very careful. Ooh, that's pointing looks like right at the 1.6 on mine. 1.6. Right. I think this is probably really close to 1.6. I say equals, I'll put 1.6 and then a little question mark, because I don't know if that's exactly true, but I think it's pretty close. You guys think? Right. Let's check with the digital calculator. What is 43 divided by 27? 1.59259. Yeah. Guess it. It's more like 1.593 about. That's really, really close to that. Guess that? Okay. 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 So you guys do see you only have so much precision. You can get two, maybe 3 digits of precision if you have a really good calculator. Okay. But then you kind of lose after that. All right. All right. You guys good? All right, how about this? Let's do multiplication. All right, you guys ready for multiplication? All right. Now multiplication is just the opposite process of division. So if you can divide, you can just do everything backwards and multiply. Okay. How about this? Let's go back to our basic example. What is 6 divided by 2? Well, it's 3 over 1. It's the same thing. Right? Can I cross multiply? Can I cross multiply that right there and that right there? Is that true? Right. So here, let me bring this over here. Bring this over here. So since I know that 3 over 1 is equal to 6 over 2, we did that a few minutes ago. I can cross multiply. Cross multiply, cross multiply. I get 3 times 2 equals 6 times 1. Or maybe I should have done that the other way. Yeah. So 1 times 6 is 3 times 2. Right? Right. Either way. Is that okay? Okay. Okay. So what are we going to do with that? Well, suppose I want to multiply 2 numbers. What I'm going to do is set up in such a way. Here, go back to my fraction form. Say I want to multiply 3 and 2. What is 3 times 2? I don't even know what 3 times 2 is. I'm going to find out. Okay. So my inside 1 is going to point to one of the numbers I'm going to multiply. Let's say 3, for example. And then I'm going to search around. I can multiply anything by 3 now. I can multiply anything by 3. All right, so let me line the calculator so it looks like that. So the inside 1 is pointing to the outside 3. So I have 3 to 1 ratio. Right? What that means is I can multiply 3 by anything I want right now. So I'm going to search around on the inside track. Let's say I want to do times 2. So where does the 2 point to? Hey, it points to 6. And that'll be the answer. Right? Right. So let me say that again. So I want to multiply 3 times 2. So I line the inside 1 to the outside 3. So now I can multiply anything by 3. 3 times what? How about 3 times 2? So go on the inside track and look for the number 2. And that will point to the answer. And the answer is, in this case, 6. Okay? So be like that. Right, guys, that? Let's try it with these 2 random numbers here, like 43 and 27. Wonder what is 43 times 27 equals, right? We're going to use the same method and see if we get it. Right. So first of all, order of magnitude. Well, I know 40 times 20 was that like 800? Right. So I'm going to guess this is probably getting up towards 1,000 or so. Right. So I know it's not 10 or 100, but it's probably pretty close to 1,000, you guys think? Okay. I know the last digit has to be a 1, because 7 times 3 is 21. Right. Let's say I'm bad at multiplication. I just know that so far. Right. So I need the inside 1, I'm going to align with the 43. So the inside 1 is aligned with 43. 41, 2, 3, that's right there. Bam. Remember, 4.3 and 43 are the same number on this calculator, but the decimal float. You guys got that? The inside 1 and the 43? Right. Then I'm going to search around for 27 on the inside track. 27 is right here. Bam. There's 27. And it points to the answer to this question. Oh, actually, it looks like it's going to be a little over 1,000. Huh. Okay. Right. Right. So I'm looking at what is that? 1. It's between 1,100 and 1,200. Probably a little closer to 1,200. I'm gonna guess. How about 1,161? I'll put a question mark. I don't know. That's right. Okay. It's like a little more than halfway between 1,100 and 1,200. Okay. All right. Let's see. What does the digital calculator say? What is 43 times 27? That's exactly it. Okay. It's 1,161 exactly. Okay. So bing, got 1,161. Okay. All right, so you can multiply. Now you guys can take square roots and divide and multiply with just these circles right here. Right, you guys see that? All right. Questions so far? All right, let me show you guys one more trick. This is not the circle calculator, but show you guys another way to multiply. Let's do 43 and 27 again. Right. So let's 43 times 27. Show you guys a cool trick here. You can multiply any 2-digit numbers together. Right. So do you guys remember from algebra, FOIL, FOIL? Right. You can actually take advantage of that and multiply any 2-digit numbers really fast. Right. So it's like this. If you have something plus something, multiply by something plus something. Okay. Right. You can do here. If I do like A plus B and C plus D and multiply it. Okay. First is A times C. Outside is AD. Inside is BC. Last is BD. Right. So if you have any crazy variables, this and this are the same thing. Right? This is a FOIL expansion. right, so what does that have to do with this? Well, I can sort of think of this like that. I can think of this like 40 plus 3 and 20 plus 7, right? Also, I'm going to start with last, and I'm going to work backwards. So like last, inside, outside, and then first. Okay. All right. So watch this, guys. What's 7 times 3? 21. All right. So you got to know times tables up to 10%. All right. So I'm going to write down 1, but I'm going to carry a 2. Okay, because 21. So I wrote down 1. I'm carrying a 2. Is that okay? Okay. Let's do outside, inside. What's 4 times 7? 28. What's 3 times 2? 6. And I carried a 2. Is that true? So like 36. Okay. So I'm going to write down 6 and carry the 3. Okay. What's 4 times 2? 8. Plus I carried the 3. So like 11. Is that 1161? Right? Is that the same thing as this guy was showing? The same thing as the digital calculator was showing? There you go. Now you got multiple ways to multiply numbers. Okay. All right, you guys good? All right. All right, let's do one more for fun, because I think we got a little time here. All right, how about 23 times 89? Something crazy. 23 times 89. Let's see if this works. All right, what's 3 times 9? 27. 7. Carry the 2. Right. What's 2 times 9? 15. What's 3 times 8? 24. Plus the 2 I carried. That's like 14. It's like 44. So write down the 4, carry the 4. 2 times 8 is 16. Plus 4 is 20. 2047, I'm going to say. Let's see, how does that hold up on this calculator? So I need the inside 23. No, sorry. No, the inside 1 points to the outside 23. Inside 1, outside 23. Bam, that's right there. Okay. And then I want to multiply 23 by 89. So let me search around where's 89 on the inside. That's right here. Bam, is 89. That points to, it's a shade over 2. It's between 2 and 2.1. Hey, it's between 2 and 2.1. Of course, 3 decimal places over. Okay. And finally, let's do the digital check. 23 times 89. Yep, 2047. So there you go. There's 3 different ways to multiply those numbers. All right. We're up on today. Again, here, just trig puzzles. If you guys turn these in today, awesome. If you've got any students out there who are really struggling on this, then you guys got one more. You guys can take it home tonight and keep working on those. All right, so we got this going on. We got this going on. You guys got some algebra. All right, and if you guys got any questions, of course, you can always ask me and I'll help you out too.